Section 8.1. Alright, let's have a discussion about how our confidence interval formula would change if instead of wanting to be 95.45% confidence, we wanted to go with some other level. So the key to making a change is to figure out where did we come up with this 95.45% confidence level, and that was from the empirical rule. That was the amount of area that was within 2 standard deviations of the mean, and that's why we have the 2 right here. So since this is the number of standard deviations, and that this came from the empirical rule, there's a couple quick changes that would fit right along with that. If we wanted to go to a 68.27% confidence interval, then based on the empirical rule, instead of going out 2 standard deviations, we'd want to go out 1 standard deviation in each direction. And another change that would come from the empirical rule is if we wanted to have a 99.73% confidence level, then we would need to go out 3 standard deviations in each direction. So this number right here would become a 3. So that gives us some options, but the problem is nobody that does statistics really does a 95.45% interval or a 68.27% or a 99.73% interval because all 3 of those numbers are very messy. The typical confidence levels that we use in statistics are either 90%, 95%, or 99%. And when we think about, well, what are we going to put here for that, we just have to think back to what is this 2 and where did it come from. That was the number of standard deviations you would have to go out on the standard normal curve to get an area of 0.9545 in the middle. So what we want to put in these 2 spots is the number of standard deviations you'd have to go out under the standard normal curve to get 90% in the middle. Those would be z-scores, and that makes it a working backwards question. Let's look at a picture for that. So we draw our bell-shaped z-curve. We put 90% of the area in the middle. That means 10% of the area is left over, but that has to be split among the 2 sides. So half of that 10%, or 0.05, would go on each side. And then we'd want to think about what z-scores make that happen. There's one on the left, which would be a negative value. There's another one on the right, which would be a positive one. And we can use our calculator to sort out what those would be. I would probably find this one. So the negative z would come from doing inverse normal of the area to its left, which is this 0.05. So we can put that into the calculator, go to the distribution menu, go to inverse normal, enter an area of 0.05. We should get a negative z-score, which in this case would be negative 1.645. So that's my left z-score, and the one on the right I could do something similar, but I could also just use symmetry and say this one's going to be 1.645. So my argument is, if you want to be 90% confident instead of 95.45% confident, you should go 1.645 standard deviations to the left of your point estimate p hat, and you should go 1.645 standard deviations to the right of your point estimate p hat instead of going 2 standard deviations, which makes the 95.45%. And it makes sense that we want to have a little bit smaller area. We don't go out quite as far as we do when we want the 95.45. So this procedure right here is what we would follow every time they give us a different level of confidence. So over here we're just going to work on some notation a little bit. The kind of generic confidence interval, or the placeholder for confidence level, is 1 minus alpha. That's a little bit strange that it has the 1 minus. The reason for that has to do more with the next chapter than this one, so that's something that I'll leave out of this discussion. But they do represent the generic confidence level as 1 minus alpha. So if you think about how much area that's been used up in the middle, 1 represents all the area. So I would say in the middle we have all the area except for alpha. So the area that's still left over after you go in the middle is alpha. Again, we have everything in the middle, 1, except for alpha. So there's still alpha left over for the outsides, and you'd put alpha over 2 on each side. So what we generally do is say that the z-score you want right here, we're just going to call it z-star, and this one by symmetry would be negative z-star. The way you would find these z-stars on any specific problem would always look like this, because you're going to be given an area, and you'll be able to put that specific area there, be able to put specific numbers on the outside and use inverse normal. But as just a placeholder in our formula, instead of putting the 1.645 or the 1, 2, or 3, we're going to put this z star number. So this is going to be our generic formula for a confidence level that says if your confidence level is 1 minus alpha, you have to find the z star distance to go out in each direction. And again, that looks pretty abstract, maybe even a little scary, but it's always going to be a specific problem for you that looks more like this side. Alright, let's go ahead and look at an example that uses this new 90% confidence level that we developed right up here. So studies are performed to estimate the percentage of the nation's 10 million asthmatics that are allergic to sulfites. In one survey, 38 of 500 randomly selected U.S. asthmatics were found to be allergic to sulfites. Find a 90% confidence interval for the true proportion of all U.S. asthmatics that are allergic to sulfites. So the first thing on a problem like this is to determine is it about a mean or proportion, and they want us to do a confidence interval for the true proportion. So this is going to be our formula right here, that P will be somewhere in between P hat plus or minus z star times the square root of p hat q hat over n. Those are going to be our boundaries. So I'm going to start off by writing that formula down. We're going to want to figure out what is p hat plus or minus some z star times the square root of p hat times q hat over n. So we've got to figure out all of these pieces. So let's go over here and start working on them. First of all, I'll do the z star. We actually already did it up above, but I just want this to be a complete example. So let me show you again. If they want us to be 90% confident, then that's going to be the area that goes in the middle, which I would write as 0.90. And then I would think about how much area is left over. That would be 10%. So 5% on each side. I would want to find the two z-scores. There's a negative z and a positive z. And if I do inverse normal of 0.05 on the calculator, that's going to give me this negative z-score right here. We just did that on the calculator a moment ago, so I'll just write down the answer. It's negative 1.645. And that means our positive z, and I guess you could say these are our z stars, is positive 1.645. So those are our z-scores. Now how about the other pieces we need? We need p hat, and we need q hat, and we need n. Well, p hat is the proportion of successes in your sample. That's x over n. And as we read this problem, it says that 38 of 500 selected were found to be allergic to sulfites. So 38 is the number of successes we had, 500 is the sample size, and we can divide that to see what it is as a decimal. So 38 over 500 gives a sample proportion of 0.076. We usually write our proportions with 4 decimals, so even when it comes out exact, I usually will add that fourth one. Our plus or minus piece is almost always messy, and we're supposed to match that with this number, and yet those rounded numbers should have at least 4 decimals, so I just put the 0 here to remind me of that. So a couple other quick things we can squeeze in then to this spot. Q hat is 1 minus p hat. So if you do 1 minus the 0.0760, you get 0.9240. And we could make one other piece in our list. The n was that denominator right there, which is 500. So now we have every piece we need. We know the p hat, 0.0760, and we know the z star, that's the 1.645, and we know our q hat from the 1 minus and the n from the sample size. So now let's take a look at the work over here, finishing off our confidence interval. So we start off with our point estimate. In our sample, 0.0760 was the proportion that were allergic to sulfites, but that's just from a sample, so we don't have much confidence that that is correct. In fact, it's almost certain that that's wrong, so we have to give ourselves some room for error, and we're going to go out 1.645 standard deviations away from our estimate to create that room for error. So the p hat and the q hat go underneath the square root, so that's our 0.076 times our 0.924. I left the zeros off here just because of room. You could write them or not write them. The calculator doesn't care about those. And then divided by the sample size, which is 500. I left the zeros off here, but I did put them in this spot because I'm always looking to match this plus or minus piece with what I have over here, so I want that reminder that that should be 4 decimals right there for me. So this would be 0.0760 plus or minus, and now I want to work out what is that plus or minus piece. So let me bring the calculator in. and 1.645 times the square root of 0.076 times 0.924, all divided by 500. And I'm going to match that to this one, so 4 decimal places, so that'll be 0.0195. Alright, so this is my original estimate, but I don't have any confidence that that's right. I need to give myself some room for error. It looks like I'm going to give myself about plus or minus 2% here. And so I'm going to do the subtraction and the addition to find out what those boundaries are. I'm going to bring the calculator back in. So 0.0760 minus 0.0195, that's the left boundary. If I do second enter and change that minus to a plus, I get the right hand boundary. And so the left hand boundary I'll write on the left, 0.0565. And then on the right hand side, the 0.0955. And that's the interval, but we always want to remember what were we doing the confidence interval for. They asked what was the true proportion for all U.S. asthmatics. So we found a p-hat of 0.0760. That's a sample proportion. The true proportion is a reference to the population proportion, and that's reinforced by the word all, and the symbol for a population proportion is not p-hat but p. So I think that the true proportion of U.S. asthmatics that are allergic to sulfites, which is p, is an element of this interval that goes from 0.0565 to 0.0955. Since I have all this scratch work over here, I should probably go ahead and box my answer, so let me do that. Alright, so let's look at the steps that we just went through to do that confidence interval, and these are the ones that we would apply as we go forward. First of all, for the requirements, we need this bell-shaped curve to really be there, and for that to happen you need p-hat to be approximately normal, and we learned in Chapter 7 that that happens as long as both NP and NQ are both at least 10. Now here it doesn't say NP and NQ, it says X and N minus X, but the rule is still the same. We want those to be at least 10. I'll show you why they look like that in just a moment. And then for a confidence level of 1 minus alpha, we want to use inverse normal to find the two z-scores that trap an area of 1 minus alpha in the middle with two equal outside areas. Now that is the most kind of confusing sounding part because of the 1 minus alpha, but they gave us a confidence level in this problem, and they'll do it in all of them. So when they say 90% confidence, we know our 1 minus alpha is 0.90, and we write that in the middle. And then we just think about how much area is left over. And then we use inverse normal to find those two z-scores, right? And that's what we did. And then our confidence interval for p is our point estimate p-hat plus or minus our z-star times the square root of p-hat q-hat over n. And remember to match decimals with the plus or minus piece when you do that. Alright, so just a quick comment on why is this an x and not np. It really is supposed to be np that's bigger than 10, but we don't know what p is. So, right, we're trying to do a confidence interval to estimate that. Our best guess at what p would be is p-hat, and p-hat is x over n, and when you do that, the two n values cancel off, and you just get an x. And so, even though you're supposed to be checking is NP at least 10, our best guess at what NP is turns out to be X. So that's why that's replaced it in that spot. And it turns out that if you do NQ and work through the same math, you end up with N minus X. So that's why we have that other piece there like we do. Alright, let's go ahead and practice that new formula and procedure by just going back to this problem we just did about the proportion of all U.S. asthmatics that are allergic to sulfites. But this time we're going to use a 95% confidence interval just to see how that changes things. So all of our pieces are going to remain the same as they were in the last problem. So I'll just make a quick list of what we're going to do here. We want the p-hat plus or minus z-star times the square root of p-hat q-hat over n. So the p-hat, q-hat, and n are still the same as what we just did in the last problem, but anytime you change your confidence level, what that affects is your z-score. So let's go figure out what the z-score would be for that by drawing a little picture over here. So we draw our bell-shaped curve. This time we'd say that the area in the middle is 0.95. That leaves 0.05 left over for the outsides, but that's the total for the outsides. On each side we only get half of that, so half of the 0.05 would be 0.025. So when you go to find your z star, which technically is this one over here, it's usually easier to find the negative value on the left because you know the area to the left of that one. So negative z star is inverse normal of 0.025, and we can go to the calculator for that. So we bring that in. So we would go to the distribution menu, we would choose inverse normal of 0.025. We should get a negative value here because we're working on the one on the left, and we get negative 1.960. It's at 59, but the 59 is followed by another 9, so round that up to 60. And remember, always 3 decimal places on our z-scores. And so that means the z-star that we're going to use in the formula is the positive version, 1.960. Alright, so let's look at what that does to our formula. As I said a moment ago, we still have the same p-hat that we did on the previous page, so that's 0.0760. And now for the plus or minus piece, instead of going out 1.645 standard deviations, we want a little bit more confidence, so we want to go out a little wider, 1.960. And then we still need that square root piece. So that would be the p-hat, 0.076, times the q-hat, 1 minus that, which is 0.924. And all of that is over the sample size, which was 500. Copy down your point estimate again, 0.0760, and then figure out what the plus or minus piece is on the calculator. So let me bring that back in and work out that plus or minus piece. So we have 1.960 times the square root of, let's see, blocking that a little bit. So 0.076 times 0.924 divided by 500. Almost the same calculation we did on the last one, just a different z-score because we want a higher level of confidence. And the plus or minus piece is 0.0232, if I round that to 4 decimals to match this piece. So let's write that in there. And then we do the addition subtraction, and that would give us our confidence interval for p. So first the minus, then the plus. So let's do both of those. 0.0760 minus 0.0232. That's the left boundary, and then again with the plus gives us our right boundary. So the left boundary of our interval is 0.0528, and the right boundary is 0.0992. Help me fill those in. And then again, just to be clear where the answer is, I'll go ahead and box that piece. So why did we repeat the exact same problem twice? Well, almost the exact same problem. And the reason was to see what the effect is on raising your confidence level. So our confidence interval, we had to give ourselves some room for error. We went out almost 2% in each direction and got this interval. But when we wanted to be 95% confident, what happened with our room for error is we had to give ourselves a little bit more than 2%, and that created a little bit of a wider interval. And that give and take between confidence level and the plus or minus piece, and therefore the width of your interval, is always going to be there. So let's make a note of that. And the note is that for a fixed sample size, the larger the confidence level, the wider the interval, and then that's true the other way around as well. If you were to lower your confidence interval, you would get a narrower interval. And no one really wants to ever lower their confidence level, right? Like, why would they say, oh, I'm too confident, I want to be less confident? But sometimes people don't like how wide their interval is, so they might try and make it narrower. So what we have to realize is for a fixed sample size, if we try and make our our interval narrower, then our confidence level is going to decrease. So there's a give and take there. We do like high confidence, but we don't like wide intervals, and we try and find a balance there. And the analogy to this is if you want to be more confident that you'll catch a butterfly, then you need to make your net bigger. And I always think about little kids there trying to catch a butterfly in their hand, and they don't have very much success at it because the butterfly flies kind of erratically. Their motor skills maybe aren't so great, and then plus their hand is just small. But if you gave them a net, then the butterfly is probably in trouble, right? Because they don't have to hit when they swing the net, they don't have to have the butterfly right in the middle of that opening. As long as it's anywhere in the opening, they're going to catch it. So here's the middle of our net. It's our p hat, and it probably misses, but that's okay because we're giving ourselves some room for error and creating this wider net to try and catch the right answer. According to a Pew Research poll, 34% of adult Americans report that they are happy. A recent sample of 391 regular churchgoers revealed that 168 of them were happy. Comment on the requirements for finding a confidence interval for the true proportion of all regular churchgoers that are happy. Alright, so when we start thinking about the requirements, we want to think about what type of problem we're doing. This is a confidence interval for a proportion. And for a proportion problem, we're back to that idea of needing NP and NQ to be at least 10. And we've seen that the way we check that with proportion problems is to look at the number of successes and failures. In this problem, they looked at a sample size of 391, and they saw 168 successes there, 168 happy folks. So that's our x right there. So x is equal to 168. And that's greater than or equal to 10, so that takes care of part of our requirement. And then we also need at least 10 failures in our sample, and to look at that we look at n minus x, and we have a sample of 391, so that's our n. So n minus x is 391 minus 168, and that would be 200 and something. Certainly it would be bigger than or equal to 10. So because both of those are at least 10, that implies that p hat is approximately normal. And if p hat is approximately normal, that implies that the requirements are met. So we're good to go on this one. Alright, so moving on to part B, obtain a 99% confidence interval for the true proportion of all regular churchgoers that are happy. So again, we're talking about a proportion problem. So our proportion problems have the formula for a confidence interval of p hat plus or minus a z star times the square root of p hat times q hat over n. So we want to assemble all these pieces and plug them in. I'm going to go ahead and start off with the z star portion of that. So I'll want to draw a picture representing this 99% confidence level. So draw our normal curve in and put 99% in the middle. That leaves 1% left over, but we'd split that in half among the two sides, so that would be 0.5% or 0.005 on each side. And then this is a z-score that we're looking for. So I'll find this one over here, this negative z. Negative z would be found by doing inverse normal of the area to the left, which would be 0.005. So let me go ahead and bring in the calculator for that. I want to use the distribution menu, inverse normal, and we have 0.005 as the area in our tail. So that gives us negative 2.576. And that's actually the negative z-score over here, so the positive one, which officially is our z-star, by symmetry would be 2.576. So I'm going to plug that in right there. And then there's some other stuff that we need to kind of gather as well. We need to know what our p hat is. And they don't give p hat, but they did say that we had 168 successes out of 391 tries. So p hat would be 168 over 391, and I'll just do that division off on the side. And I get 0.42. It's a 9.6, but needs to be rounded up, so that would be 9.7. So that's my p hat. And then q hat would just be 1 minus that. So q hat would be 1 minus p hat, which would be 0.5703. So now we have our p hat, we have our z star, and we know our sample size n was 391. So we have everything we need to plug into that formula, so I'm going to start working on that. So my p hat was 0.4297 plus or minus this z-score or z-star of 2.576 times the square root of my p hat, 0.4297, times 1 minus that, or q hat, which would be 5703, and all of that is divided by my sample size, which was 391. Alright, and when we do this type of confidence interval, or any type of confidence interval really, we always want to show the answer to this plus or minus piece, and we'll see why as we go on to the next page. Let's go ahead and keep that work going. So this is 0.4297, and I want to figure out this plus or minus piece right here. So let me plug that into the calculator. So let's see, we have 2.576 times the square root. The calculator opens the parentheses, and I want to make sure I do not close that until after I have all three of those numbers entered in. So I've entered the p hat, the q hat, and the over n, and then I close the parentheses. And I always want to match the decimal places on the plus or minus piece with my point estimate, which is p hat here. This had 1, 2, 3, 4. So I'll put 0.064, and the next digit is a 4, but followed by an 8, so I'll round that up to a 5. And then finally I just do the plus or minus to get my confidence interval. So 4297 minus the 0.0645 gives me a left boundary of 0.3652. And I do that with the plus, and I get the right boundary, which is 0.4942. And then what were we doing a confidence interval for in the first place? We were trying to find a confidence interval for the true proportion, and the symbol for the true proportion, or the population proportion, is p. So I'm going to say that I'm 99% confident that p is an element of this interval that goes from 0.3652 to 0.4942. Okay, continuing on with our problem about the happy churchgoers, let's look at part C. So based on this interval, can we be 99% confident that the true proportion of churchgoers that are happy is higher than the 34% found for Americans in general that are happy, and explain. So on the beginning of the previous problem, they said that the study had found that 34% of all Americans were happy. The interval we just found is just for the churchgoers. Let's bring that back in for a moment. So there's that interval, and just talking it through, and then I'll write it out. If the proportion of churchgoers that are happy is somewhere in this range, then it could be as low as 36.5%, or as high as 49.5%, or anywhere in between. But if you're in between 36.5 and 49.5, then you're higher than 34%. So it does look like we can say yes to that. So I'm going to say if p is an element of that interval that we found on the last part, 0.3652 to 0.4942, then that implies that p is greater than 0.34. And that's the 34% number right there. So if p is anywhere in that range, then that implies p is greater than 0.34. So can I be confident in that? I'm going to say yes. So a confidence interval should be considered a list of all of the reasonable possibilities for the population proportion. I said the word if here because I don't know for certain that p is in this interval, but I'm confident that it's in there. These are the things that are reasonable possibilities for p, and all of those reasonable possibilities provide a yes. So when our entire interval is a yes to the question, that's when we can say yes based on that interval. Alright, let's go ahead and continue on. So is it likely that the point estimate in this problem is exactly correct? This is a question that we've seen over and over again. Is it likely? I'm going to take that to be a probability question. And the point estimate, that is the value from our sample, so that was p hat. And is that exactly correct would be meaning when we use it as an estimate, is it exactly equal to the population proportion? So I would translate their question as what's the probability that p hat is exactly equal to p? And we've said over and over again in Chapter 7 that there was basically no chance of that. So since the chance is 0, is it likely? I'd have to say no. So the interesting thing about that is we're doing these confidence intervals, but we have to keep in mind that when you think about just the point estimate by itself, there's basically no chance you have the right answer. When we go to the interval, then we think that we do have the right answer. So how are we going from no chance of having the right answer to being 99% confident that we have the right answer? And the explanation for that is when we do it this way, we've given ourselves some room for error. So when they say how close do we think p hat is to p, what I'm always going to answer for that is the plus or minus piece from my interval. This was my p hat, or my point estimate, that I have no faith in that being correct. But once I added and subtracted 0.0645 to that to create this interval, now all of a sudden I was 99% confident that I had the right answer. So in order for that to make sense, I must have felt that the truth was within this distance of my estimate, because I didn't think the estimate was right, but when I went this far in each direction, then I was very confident I had it. So when we get to ask this question, how close do we think p hat is to p, we would give that plus or minus portion of our calculation, which is one of the reasons why it was good that we showed that in our work. So how close do we think p hat is to p? I would say that I think it's within 0.0645, and then I should put units on that. Well, I guess that's just a proportion. I could say within 0.0645, or I could say within 6.45%. So you could say that we gave an estimate that 42.97% of the churchgoers were happy, but we might be off by 6.45% with that point estimate. But once we give ourselves that room for error, all of a sudden we're 99% confident that we've got it. So because this is the room we give ourselves for error, we give that a special name. That's called the margin of error, something you've probably heard of before. When you see the news on political polls and opinion polls, they often state the margin of error. So that's the value that we add and subtract from the point estimate to create our confidence interval. That's called the margin of error. And just again, that summary of the logic, we know that p hat does not equal p, so we must give ourselves some margin for error, and in this section the margin of error is given by the formula below. Margin of error, we'll use a capital E for that, is z star times the square root of p hat q hat over n. And if you think about the formula that we use, that makes sense, because we're saying that the margin of error is the part we add and subtract. And if you go back and look at the original formula, we have p hat, and then we add and subtract z star times the square root of p hat q hat over n. So this piece right here is our addition subtraction piece, and so it makes sense that that would be our margin of error as well. All right, that wraps up section 8.1.